Hi, this is Blair Allen. I'm with Egg Medical. I'm here with Dr. Robert Wilson, who's the founder of Egg Medical. We're going to conduct a virtual demonstration of our system. We're going to show you some data on scatter radiation in the cath lab and what we learned about the scatter cloud. We're going to also go through the system behind us and do a demo of that system, and then how that system will reduce the amount of scatter radiation in the cath lab. So with that, let me turn over to Dr. Bob Wilson. He is the founder. He's also an interventional cardiologist, a former cath lab director down at the University of Minnesota, and also the founder of Assist Medical Systems. Great.
All right, well, thanks, Blair. Well, as Blair said, I'm an interventional cardiologist, and I would say I've been over 30 years. I've been an average user of radiation shielding. I use it when it's convenient, and when it's not convenient, it tends to get flung out of the way, or if the patient gets sick, shielding goes out of the way. And you know, as you get older, you have friends who have lymphoma or leukemia or multiple myeloma. We have melanoma on the foot. A couple nurses with cataracts in their 40s, and you know, you wish you had been better with the shielding, and you realize the reason you weren't is because the shielding is cumbersome to use. It doesn't move with the patient, it doesn't move with the x-ray system, and so it tends to get discarded or not optimally used when it should. So to me, this seemed like a big mechanical engineering project. We ought to be able to protect everybody in the room with a shielding system that moves with the x-ray and moves with the patient. And so we started out on this journey about 4 years ago, and the first thing we had to figure out was, you know, where the scatter cloud really is. And you know, there's some published data, but it really wasn't granular enough to be able to design a system that was going to be able to reduce scatter radiation in the room by 90%. And so the first thing we did was we got a Phantom from the Department of Energy. Well, it looks like a person, scatters like a person, probably about an 80 kilo person roughly. We got that Phantom and we put that on an x-ray table, and then we measured scatter radiation at 6 points around that table where people typically stand. And in each one of those positions we measured from the floor to 2 meters up every 20 centimeters. So we got an idea of the circumferential distribution of the cloud and also the vertical distribution. So I'm going to show a little of that data right now. So if you look on this diagram, you can see the 6 positions around the table where we typically measure, where the echocardiographer stands for structural heart, where the anesthesia or right heart cath person would stand over the right shoulder, where you are at the patient right chest for pericardiocentesis or biopsies or subclavian access, where the angiographer stands for femoral or radial access, and then next to the angiographer where the assistant is, and then finally where the nurse stands about 1.5 meters away from the table. And if you look at the histogram on the left here, you can see the scatter radiation levels for each of those positions around the table. The blue bars are the average scatter radiation measured from the floor to 2 meters up, and the yellow bars are the peak dose measured anywhere in that 2 meter height. Typically that's around the mattress or just below the mattress. So I think the first thing that's striking is that the highest doses are around the head. And that's the place where right now we have the least amount of shielding. There's no rail around the table to provide shielding below the table, and it's very difficult to work around the hanging shield from that area. So we were going to have to be able to shield those areas effectively. The next position is the angiographer position, which is the next worst. The place to be is the assistant, who is next to the angiographer. That actually has the lowest dose of any place in the lab. And then the nurse, who is 1.5 meters away from the patient, is actually getting more radiation than the assistant is next to the angiographer. So we knew we were going to have to be able to protect that. So that's where we started. So the next issue was the vertical distribution. You can see that shown here. Again, this is for all 6 positions around the table, floor to 2 meters up every 20 centimeters. And in this, we set the table at 1 meter. And what you can see from this diagram is that the scatter radiation measurements shown in the blue bars show us that the bulk of the scatter radiation in all those positions is tabletop and below. That makes some sense because most ricochets either go lateral, they go down, they don't go up. The degree of scatter radiation below the table varies a little bit from position to position. On average, it's about 69% is below the table, and about 31% is above the table. But again, that varies a little bit from spot to spot around the table. So Blair is going to talk a little bit about how we took this information and designed the system that we currently have. And then I'm going to come back a little bit and tell you about the effectiveness in the system in that same model of reducing scatter radiation throughout the room.
Okay, so this is the EggNest system. Now we start with a carbon fiber platform, which is really important because as we learned, 70% of scattered radiation is on the table. We have to have a means or mechanism to block that scattered radiation. And this carbon fiber platform replaces the patient mattress. It's very strong, it's radiolucent, and it's light. And we're able to attach a railing system to it. We're able to integrate shielding and a mattress. So that will replace the patient mattress on the table. Now, as you can see here, this system is really designed to be modular. I have many of the components folded down. They're usually folded down for patient loading, then folded up after you put the sterile drape on the patient. And so let me go through each of these elements. So here we have on the right side, and it starts here, it goes all the way over to the left side, is our flex shielding below the table. And you can see it has a curvature nature that brings a center of gravity under the table and allows it to move and swing with the X-ray gantry. And so in it we've attached these stays that hold that form and that shape. And you can see the curvature nature, and it attaches to our railing system here. We have components that go all the way around, and they can be easily attached to these rails and removed if needed. Above the table, where we're seeing a lot of scatter radiation, we have what we call flip shields that provide protection for the operator and for other staff members in the room. Now these flip shields, we start with the arm board. We have a post that goes into the post holder. These are radiolucent. The arm board's radiolucent if you ever need to image through it, and then radioprotective here. And it's designed to be able to flip down for patient loading, or it would be up after patient loading. You can do radial access at 90 degrees. We can have radial access at 30 degrees, and this part of the system will come out, provide protection here for the operator, and it can be slid in as well. But like I mentioned earlier, it's down for patient loading. Down here we have the workbench. This provides radiation protection for the lower part of the torso. We see our rail system here. This is quickly, easily detached there. Like I said, it's designed to stay on the table. It can be flipped up, provide extra work area. Your controls would be somewhere around here. It's very radioprotective and blocks in that radiation off of the lower torso. Again, you can easily fold up and down. At the head of the table, where we see the most scattered radiation in the lab, and the highest doses we saw was coming from the patient's pillow, we've designed a pillow shield that can fold up and down near the patient's head, doesn't interfere with the C-arm, and we'll have wings here that come out and provide really good protection for structural heart cases, the nurses coming up talking to the patient, device implants, etc. The next thing I want to show you is our spot shield. This is designed to work with your hanging shield. It is attached to the railing system on the other side of the table. It can move up and down, and will move with the patient as the sled is moved. And the hanging shield will come here. This provides a lot of protection for any radiation coming off of the patient's abdomen or ephemeral access site. So this is a really important feature in helping reduce scattered radiation in the lab. The last thing I want to show is our radiation meter. This is an instantaneous radiation meter that we use when we do evaluations. And we can collect radiation from the right side of the table or the left side of the table and then compare it to the other side. So it's something we like to use in our demonstrations. This is our system.
I want to talk now a little bit about the effectiveness of the EggNest system in reducing room scatter radiation. So we use a standard setup with a C-arm X-ray, 70 keV fluoroscopy, a standard meter, and the phantom that I talked about before. And so if you look here on this next slide, what you can see is the effectiveness of the EggNest compared to standard shielding, which is a hanging shield and a table skirt that everybody uses. The effectiveness of the EggNest in reducing scatter radiation in each of the positions around the table. The standard shielding radiation measurements from floor to 2 meters up are shown in blue and the EggNest in green. And you can see that around the table, the average reduction in dose is about 91%. It varies a little bit from position to position. And we're not saying that standard shielding doesn't work. It does work. If you look in the lower right-hand diagram where it says assistant, you can see that from the floor up to about 80 centimeters, there's a significant suppression of scatter radiation by the table skirt. The problem is it just doesn't do much above that, and so the person in that position is still relatively exposed. And by the same token, in the angiographer position in the lower left, you can see, if you look from about 120 centimeters north, that the hanging shield works. It's suppressing scatter radiation in that zone, but once you get below that, the patient and the mattress, and just below the mattress and then below the table skirt, you still have significant leakage of radiation, and that significantly increases dose. Right, so the next thing we wanted to do is we wanted to get a sense of the effective angulation on X-ray dose and the effectiveness of the system in suppressing scatter radiation in the room in various angulated positions which are typically used. So that's what's shown here. We needed to get an index of total room scatter. We did that by adding up all of the scatter radiation measurements from floor to 2 meters up in all 6 positions around the table, and that's what's shown here. If you look on the left-hand part of that histogram where it says PA projection, the no shielding scatter radiation volume of the room is shown in dark blue. In light blue is with standard shielding, the hanging shield and the table skirt, and the EggNest in green. And you can see that although standard shielding has a modest effect on total room scatter, it's really not that great. And the reason is it's not made to suppress total room scatter where the EggNest is. As you angulate the X-ray, you can see how much the dose in the room goes up. And when you get out to the iliocaudal view, you can see that there's almost a 4-fold increase in scatter radiation compared to the PA projection. And then you can see the effect of standard shielding, which is fairly small, and the EggNest, which again gives a little over 90% protection even in that view. And so that's our data. About a 91% reduction in scatter radiation throughout the room. Varies a little bit from angle to angle and position to position, but all within that relative frame. So we think we've achieved our goal of suppressing scatter radiation in the room and making it into a much healthier environment for everybody.